All right, let's take a look in this video at the math behind the recent force table equilibrium lab that we did. So if you remember, we had the force table and you were charged with taking 3 different masses and putting them at whatever angles were needed to put the center ring in equilibrium where all 3 forces canceled out. Now there's endless possibilities for how you could do this, but let's take a look at the numbers for one specific situation here. So we'll take a look as if we had 150 gram mass pulling to the right at a 40-degree angle, a 225 gram mass pulling at a 130-degree angle, and a 270 gram mass pulling at a 276-degree angle. So we'll take a look at the math for this one here, and then you and your partners can do the math for your lab to see how the math supports the equilibrium that you know you created. So keeping in mind, we know that if we have equilibrium, either there's no forces acting on an object or all the forces cancel out. So if all the forces cancel out, and force is a vector quantity, so direction matters, that means the sum of the forces in the x direction should equal 0, the sum of the forces in the y direction should equal 0. And from here, we can then now take a look at our specific masses. And the first thing I want to do just logistically is convert these masses to weights, because weight is a force. So the math proportion would work out either way, but just to reinforce our understanding of forces. So remember, if we want to find the weight of anything, we're going to take the mass in kilograms and multiply by the acceleration of gravity that's experiencing. So since we're here on Earth, it'll be 9.8 meters per second squared. So it's mass times gravity. So we'll do that for all 3 of these hanging masses. So 150 grams, well, there's 1,000 grams in a kilogram. So we have to divide this by 1,000 and convert it to kilograms. So dividing by 1,000 is the same thing as dividing by 10 3 times. So move the decimal 3 places to the left. So 150 grams is 0.150 kilograms. And then we'll multiply that by the acceleration of gravity it's experiencing on Earth times 9.8. So the weight of 150 gram mass is 1.47 newtons. And then I'll just do the calculations off screen for the 225 gram and the 270 gram. So the 225 grams is equivalent to 2.205 newtons in weight. And then finally 270 grams is 2.646 newtons. All right, so now what we're going to do is we're going to take each individual weight, and let's just call them weight 1, weight 2, weight 3. It doesn't really matter what order you break these down in, but again, if we have converted these all to weights, and all these weights are pulling in different directions, remember force is a vector quantity, so direction matters. So we can't just take them and just straight up add them or subtract them because they're not in line with each other. But what are in line are their x and y components. So for example, weight 1 pulls to the right if we get the x component of that, and combine it with weight 2's x component pulling to the left, and combine it with weight 3's small x component pulling to the right. All 3 of those horizontal x components should add up to 0 because we know these masses at these angles were put there because they put that center ring in equilibrium. So we know all the forces cancel out. So the horizontal forces have to add up to 0 and the vertical forces have to add up to 0. So big picture, if we look at this, force 1 and force 2, they're both pulling up. So the upward weight of both of those has to be canceled out by the downward weight of force 3. And force 1 and force 3 are both pulling to the right. So that weight pulling to the right has to be equal and opposite and canceled out by the one left pulling force of weight 2. So that's just kind of the big picture idea. So now let's take a look at each one individually. Again, it doesn't matter where you start. So I'll start with weight 1 here. We're going to take this and use our trigonometry skills to break it up into x and y components. So we know that it's 150 gram mass, which we converted to 1.47 newtons of weight. And that 1.47 newtons of weight was pulling a little bit to the right and a little bit up. So I'm going to call it F sub 1 x, F sub 1 y. The force of 1 in the x direction, the force of 1 in the y direction. And it was at a 40-degree angle. So we've done this before with velocity vectors. We can use trigonometry and our little SOHCAHTOA reminder about which combination of side lengths we can use to figure out each component. So relative to this 40-degree angle, this is the opposite side. Relative to the 40-degree angle, this is the adjacent side. And the longest side is the hypotenuse. So if we want to get the y component here, well, the combination of opposite side and hypotenuse, that sets up for sine. So the sine of 40 degrees equals this ratio of the opposite side length of that angle divided by the hypotenuse length. So the opposite side is unknown, that's what we're looking for. F sub 1y over the hypotenuse of 1.47. So now multiply both sides by 1.47. So force of 1 in the y direction will be exactly equal to 1.47 sine of 40 degrees, but we'll get this as an approximation just to make it a little more user-friendly. So we can do you can type it in just like you see it on the calculator. 1.47 sine of 40 degrees, making sure you're in degree mode, not radian mode. And so we'll round this to 3 decimal places, so we'll call it 0.945 newtons. So that's how much of the weight of force 1 is directed up. Now the x component is adjacent to the angle, and we know the hypotenuse, so that combination sets up for cosine. So cosine of 40 degrees equals f1x over 1.47. Multiply both sides by 1.47. So force of 1 in the x direction will end up being approximately 1.13. I went to 3 decimal places, so I'll do 3 again here. So 1.126 newtons. And just a real quick reflection before moving on. This was a 40-degree angle, so that's closer to horizontal than vertical. So the horizontal component should be bigger than the y component, and it is. All right, so with that kind of focused reminder about how to get the horizontal and vertical components of force 1, we'll go through and do force 2 and 3, but I'll try to go through those a little more quickly. So if we look at force 2 here, if we look at force 2, relative to the 0-degree mark on the force table, it's at 130 degrees. But if we're going to look at this triangle in isolation, we're just going to zoom in on this. Well, if this is the 180-degree mark and this is 130, we can label this as a 50-degree angle. So when we draw this triangle in isolation, and this is what we're calling force 2, so that weight for 225 grams is 2.205 newtons, and this is a 50-degree angle, so we'll call this F sub 2x, F sub 2y, the horizontal and vertical components of force 2. So I'm just going to go through this more quickly since we already did this one more in depth. So if we set up sine of 50 degrees, it's going to equal force of 2 in the y direction over the hypotenuse of 2.205. Multiply both sides by 2.205. So the force of 2 in the y direction, approximately, 1.689 newtons. Now we get the x component, and the x component will end up being 2.205 times cosine of 50 degrees. So approximately 1.417 newtons. And again, just a quick reflection, the y component is bigger than the x component, which should make sense because relative to the horizontal, if this weight's pulling at a 50-degree angle, it's closer to vertical than horizontal, so the larger percentage of its weight's directed up. And then finally, 3 here. If you look relative to the 0-degree mark, going all the way around at 276 degrees, so if this is 270 degrees, in terms of this being an isolated triangle, this is just a little 6-degree angle here. So this 270-gram mass is equivalent to a weight, which again, weight is force, of 2.646 newtons. So this is primarily directed downward in the y direction, so the y component should be quite a bit bigger than the x component. So this is a 6-degree angle here. So this is force 3 in the x direction, force 3 in the y direction. So if we look here, notice that this angle is done relative to the vertical here. So it's going to kind of flip-flop sine and cosine from these, where both the angles were identified in these isolated triangles relative to the horizontal. So if we look at that, it's not going to make it any more difficult. It's just going to kind of flip-flop which ones are sine and cosine. So relative to the 6-degree angle, the opposite side now is the horizontal component. So when we set up sine of 6 degrees, it's going to be the force of 3 in the x direction over the hypotenuse of 2.646. And notice in the previous 2 examples, the sine corresponded with our vertical component. So multiply both sides by 2.646. So the force of 3 in the x direction is approximately 0.277 newtons. So then the y component will involve cosine. So cosine of 6 degrees equals, that's the adjacent side to the angle, and we know the hypotenuse, so that sets up for cosine. So it's going to be the force of 3 in the y direction over 2.646. Multiply both sides by 2.646. So the force of 3 in the y direction is approximately 2.632 newtons. And again, quick reflection. Since it's only 6 degrees off of the vertical, it's almost completely vertical here, so the y component is much bigger than the x component. So again, going back to the definition of something being in equilibrium, the sum of the forces acting on it cancel out, so that means the sum of the horizontal forces have to equal 0, the sum of the vertical forces have to equal 0. So now that we've taken each of our 3 weights and broken them up into components, now let's take a look at how that math works out. Because inevitably there's a difference between the theoretical calculations on paper and what you actually got in the force table. Because of outside factors you can't fully control, like, a little bit of friction in the pulley or something like that. So let's see. The sum of forces in the x direction should equal 0. Now, when I broke down each individual weight into its horizontal and vertical components in isolation, I didn't identify any of the components as positive or negative. I just left them all kind of understood to be positive. But now that we're going to mathematically combine them, now we're going to take into account direction with positive negative signs, because force is a vector quantity and direction matters. So, sum of the forces in the x direction. So the force of 1 in the x direction plus force 2 in the x direction plus force 3 in the x direction, these three should equal 0. So let's get each of these components, add them up, and taking into account their direction with the sign. So the force of 1 in the x direction, since 1 was to the right, the convention is to the right is positive, so we'll have this component be positive, 1.126 newtons. And then force 2 in the x direction is to the left, so if to the right was positive, to the left has to be negative. So force 2 in the x direction, we're going to make this negative. So it's going to be plus negative 1.417 newtons. And then finally, force 3 in the x direction. Well, force 3 is to the right, so that x component, small as it is, that's going to be to the right, plus 0.277 newtons. So these should equal 0. Now, again, what you should probably see is the little difference between theory and reality. When you set up your force table, there's some outside factors you can't fully control, like some friction in the pulley wheels, if the string's slightly offline. So even though this should equal 0, inevitably between rounding as you did your calculations and then just some of those outside factors, it's probably going to get something close to 0, but not exactly 0. So let's see what we get here. 1.126 plus negative, or just minus 1.417 plus 0.277, and we get negative 0.014 newtons. So the sum of the forces in the x direction, which theoretically should equal 0 because we created equilibrium, we got negative 0.014 newtons. Very close to the 0 that we expected. So now let's take a look at the sum of the forces in the y direction. Again, those should equal 0. So it should be force of 1 in the y direction plus force of 2 in the y direction plus force of 3 in the y direction should equal 0. So again, taking into account directional signs, so 1 and 2 are both up, so we'll make those components positive, but then force 3 is downward, we'll make that one negative. So force of 1 in the y direction was 0.945 newtons, and that's up, so that's positive. Force of 2 in the y direction is also up, so that's positive, 1.689 newtons. And then force 3 in the y direction, since that's downward, that's going to be negative 2.632 newtons. So now let's see what those actually add up to. 0.945 newtons for force 1 plus 1.689 newtons for force 2 in the y direction plus negative, or just minus 2.632 newtons. So we get 0.002 newtons. So sum of the forces in the y direction equals 0.002 newtons. Again, theoretically, these components should each equal 0. They're very close to it, and you should get similar results when you analyze your lab. So let's see what you come up with.